Imagine searching a billion embedding vectors for the nearest match. If every vector is a raw block of floating point numbers, you simply cannot hold them all in memory, let alone scan them fast. Jegou and colleagues cracked this in 2011 with a compression trick that powers vector search at massive scale to this day. It's called product quantization, and today we're taking it apart piece by piece. Let's begin. Trace one embedding through the pipeline, and the whole idea clicks into place. Watch a fat vector shrink into a tiny code. Start with a full embedding vector, something like a 768-dimensional float array, which is roughly 3 kilobytes of raw numbers. Store a billion of those as is, and your memory budget is gone before search even begins. First move, chop that vector into several equal pieces. Each of those shorter segments, the subvectors, now gets quantized independently, and that divide and conquer split is precisely where the word product in product quantization comes from. Now quantize each piece against a small learned codebook. Every segment snaps to its nearest codebook entry, and instead of raw floats, you keep just that entry's index. The whole vector collapses into a short list of codebook indices, a compact code. Once everything is coded, distances are approximated fast using pre-computed lookup tables, what the paper calls asymmetric distance computation. That original 3 kilobyte vector now lives in roughly 100 bytes, and you can scan billions of them quickly. Really, the whole scheme rests on 3 ideas. Lock these in, and product quantization makes sense. First, splitting into pieces. Rather than quantize a huge vector all at once, you divide it into segments and handle each on its own. That decomposition is what makes the codebook small and the code short. Second, compression through codebook indices. Every segment becomes a single index into a tiny learned codebook, so a heavy float vector shrinks to a few bytes. Roughly 100 bytes in place of about 3 kilobytes. Third, fast distances from lookup tables. Pre-computing partial distances lets you approximate similarity without ever decompressing, and paired with an inverted index in the IVFPQ setup. That is what makes billion-scale search practical. Put the naive approach next to this one, and the payoff is obvious. There's a reason nobody stores raw floats at scale. Keeping raw float vectors is the honest, exact option, and it is a memory disaster. A billion embeddings balloon into terabytes, distance math crawls, and the index no longer fits on the machine you were hoping to serve it from. Compact, quantized codes flip that. Each vector becomes a tiny code, memory drops by an order of magnitude or more, and lookup tables give fast approximate distances. Combined with an inverted index in FAISS, it is the workhorse behind billion-scale similarity search. Let's tie it all together for takeaways to walk away with. Product quantization from Jegou and colleagues in 2011 compresses embeddings so you can search billions of them without storing raw floats. Each vector is split into segments, and every segment is quantized to a codebook index, turning a heavy float vector into a short compact code. Pre-computed lookup tables give fast approximate distances, and paired with an inverted index as IVFPQ, it drives billion-scale search in libraries like FAISS. All told, a heavy float vector can shrink to about 100 bytes with barely any accuracy lost. Want the rest of the vector search stack demystified the same way? Everything lives at Standarity.com. Until the next one.